All right. Okay, so thanks for joining, everyone. This is a talk titled Cobordism non-supersymmetric string theory. It's very loosely motivated by our most recent paper with my supervisor, Ralph Nicola Cribiori and Christian Nigel. Nicola is here in the audience, so good that we switch to English. And I will try to make it as pedagogical and didactic as possible, so we don't see no equation, actually. Mostly concepts that I'm introducing today, so feel free to interrupt me at any point, ask questions, and I will try to explain everything. So let me start by a brief outline. So the talk is divided in kind of 4 parts. The first is what is cobordism. It's not going to be the mathematical, strict mathematical definition, but mostly how we use it as physicists. The second part is global symmetries in quantum gravity and cancellation mechanism. These global symmetries are claimed to be inconsistent. The third part is an idea that is very related to the actual cobordism, but also to the cancellation mechanism. It's dynamical cobordism, introduced recently by the group in Madrid. And we are going to provide actually an explicit realization of this dynamical cobordism setup with a bit of more mathematical, let's say, motivation. So the last part is going to be focused on our paper and one specific example we have constructed, but let's see if we reach that part. So this is the cobordism of the main role and the new defect. Okay, so let's start with part 1. What's cobordism? The idea is that you have 2 manifolds of some fixed dimension D, and then one can say that the manifolds, let's say M1 and M2, are cobordant to each other, and we write down M1 cobordant to M2. We read it as that. When one can find some other manifold W, which is D plus 1 dimensional, such that the boundary of the W is the joint union of the initial manifolds we started with. And this effectively is a generalization of the notion of equivalence that is broader or other equivalences. And the important thing here is that you can allow for topology changes. So with this manifold W, you can have whatever one chooses to allow us and allow topology change in quantum gravity. And what is setting the restrictions on what we are allowing is pretty much physical constraints. In the strict mathematical definition, these manifolds here have more conditions. Here we only say that they are compact and of dimension D. In the mathematical definition, they also need to be smooth. But since these are going to be parallel to the manifolds on which we compactify, and we know that we compactify on singular spaces and stuff, we are not placing any such condition. So this is a bit more loose than the proper definition in math. Okay. And of course, now we have defined some equivalence classes, and we have the equivalence class of M1 being equal to the equivalence class of M2, since the cobordant manifold can be constructed. And how does it relate to quantum gravity? The whole idea is that if you start with quantum gravity, the dimensions, you compactify to the large dimensions, which is B minus K. So this K-dimensional manifold is going to be the one that is going to set what your theory is. And you have all this usual string theory landscape where you compactify on some 6-dimensional Calabi-Yau and you get some theory and some vacuum, and so on and so forth. And the idea is that string theoretical processes allow for this topology changes, so it's useful to study the whole space of manifolds, let's say, using this generalized equivalence relation. And in particular, we want to study the following group. It's the cobordism group of quantum gravity, let's say. Now, QG here is very broadly defined. And I will write down specific examples because, of course, we cannot know the structure we have to impose. Possibly to have the actual theory of quantum gravity, whatever. But we know several things that we can impose. For example, there should be spin fermions in the compactification manifold. So we can impose that the manifold is spin. Or we can say that we want our theory to be oriented. So we can impose that this group should be SON or something. But these are several possibilities we have, and I will say more later. But in any case, this group then is defined as follows. Compact K dimensional controls over this equivalent relation, which is allowed to follow. And the claim is that this thing is a group. And of course, in order to define a group, we need to have some group operation or group addition. And this is going to be, in our case, just a disjoint union. This is what holds when we don't impose any additional condition. This is the simplest thing we can do. If, for example, we have orientation, let's say, the disjoint union will be disjoint union with the reverse oriented M2, for example. But we see that this thing has no preferred ordering, so it's clear that the group we are constructing is going to be an abelian group. And you can see these like you can think, I don't know, some theory compactified on this manifold, let's say it's a Calabi-Yau, some other theory compactified here, and then this is cobordism to a different theory compactified on a different manifold of the same dimension, and this corresponds to some kind of domain wall between the theories. So here you have some theory, in between you don't know what is happening to the topology changes, anything, you don't really claim to describe what is happening there. And here you see that you have two different theories, so in principle you have some kind of folding setup that both theories converge to one. And also you need to have some zero element for the group. And now we assigned the zero element to the value. So this means that our manifold should be cobordism or Borden to zero, or it's called null Borden. And here we have nothing. Our manifold is here. So effectively, our manifold is just can be cut, can be closed. So from the d-dimensional viewpoint, so largely observer, let's say, largely dimensions, this is just a domain wall at the end of space-time that is cut off certain dimensions, and there is nothing beyond that. So maybe an effective, you can view it as an effective reduction of the number of dimensions per theory. And this is an end of the wall brain, or maybe we call it wall of nothing. These terms are going to arrive later in more complete setup, so I will explain more later. And the last thing we need is, of course, the inverse. And the inverse in this case is going to be the manifold itself, because one can see that the Cobordism class of the manifold plus the manifold itself, so two copies of the same manifold under this thing is zero. One can easily see things because you have this being m, and then you have a second. Effectively, you just can always construct a cylinder and joining the two copies. You can imagine that as some propagation in time, or not necessarily time. You can construct this type of cylinder, and here there is nothing. So this indeed is the inverse. And this is the thing that is question? No. Okay. And this is the thing that we have to be careful about orientation. Not this one. So at this point, it's okay. Let me switch. Can you hear me better now?
I think so, yes.
Okay, good. Thanks. And so up to this point, indeed, we have seen that we have some abelian group. And I think up to now it has been quite abstract. So I would like to provide some specific examples. So let's see. Let's start with some very low dimensional examples. So the easiest thing we can say is n equals 0. So now we are looking at 0 dimension manifold. So effectively we have just points. So let's say we have one manifold that is just a collection of 4 points, and then a different manifold that is just a collection of 3 points. And in this case, we see that there is no way that both manifolds are the boundaries of something, because we have this lone point that can be united with anything. On the other hand, there is the chance that we have 3 plus 3, or 4 plus 4, or so on and so forth. So in this case, everything can be united. These are all the 2 manifolds we have are the boundaries of this set of lines. So in that case, everything is fine. So if the set of 3 points was n and this was n, we had this n equals n. And also, it's the same thing as before. So effectively, if you view these 3 lines now as being bended, you can see that this is bordern to nothing. So this is 0. On the other hand, since here we have clearly 2 sets of manifolds that are in different equivalence classes, we can immediately conclude that then omega 0, so the Cobordism group of 0-dimensional manifolds, has to be Z2. And one class is corresponding to the trivial, and the other one is corresponding to the odd number of total points. The trivial one is an even number of total points. And let's go to the slightly next complicated case. And this is the one-dimensional case. So in this case, the only thing I can draw effectively is a line or a circle. And this I can always cap off with something. There is no obstruction to doing that. So this is trivial. So you can see that omega 1 is 0. And now the structure that one adds on top is what is going to play a role. Because here I'm not imposing anything, but then I would have the option to say, I want fermions to live in my theory. And if I want fermions to live in my theory, I have to allow to give a structure to the manifold. This has to be a spin manifold. This means I have to choose a spin structure. And this means that effectively when the fermion goes around the circle, I have to choose whether it picks up a minus sign or not. So now we don't only have this one circle, but we have S1P and S1A, periodic and anti-periodic. One is corresponding to Ramon boundary conditions, and the other Navier-Stokes. And it has been shown that only the circle that has the anti-periodic boundary condition is the boundary of the disk. On the other hand, the periodic circle cannot be written as the boundary of anything. It cannot inherit the periodic structure from something. So in this case, we can already say that omega 1 spin equals Z2. Once again, the trivial class is the anti-periodic one, and the non-trivial one is the periodic circle. And one says then that the periodic circle is the generator of this group. And I would just write down the whole group, let's say, for the spin structure, because this is a very common approximation we are doing for quantum gravity, since the first thing we want to require is the existence of fermions. Okay, let's say up to 8. This is Z2, which we have seen explicitly. Z2, 0, 0, 0, 0, and
so on and so forth. And if you're familiar with K-theory, one can observe immediately that up to here, up to 7 actually, this is identical to real K-theory, so KO theory. And this is known that it's classifying the D-brane charges for type 1 theory. And this is not something that is accidental, but there is a much deeper relation between Cobordism charges and D-brane charges. But I would not say much more about this, but Ralph and Nicolau have a very nice paper regarding this equivalence. So if you're interested, you can take a look at that. But in any case, it's very clear that the structure has some deep physical meaning and we can read off things from it. Okay, so up to this point, any questions?
Both open and closed manifolds? So you said that you have in one dimension, for example, you have the interval and the circle, so you consider.
Okay, I should not have the interval. The definition says that they are closed.
Okay.
To be more precise. Yes. Yes, thank you. Okay, any other question before I go on? Okay, and then I will go to the second part, which is global charges, global symmetries, let's say, in quantum gravity. Okay, so the whole idea is that quantum gravity does not admit any global symmetries. This is more or less widely accepted. There are several arguments about black hole evaporation, let's say, and I will provide one, but there are many loopholes and one can counteract this. But in any case, maybe one of the most robust conjectures in the Swampland program that they have spoken about a lot, but I wanted to not have a Swampland talk today, so is the claim that there are no global charges in quantum gravity. And the idea, the way to view this like in a quite naive way, would be to have some crude argument and say, okay, suppose there is this global symmetry, and then you have a particle charge under the symmetry, it has a charge Q, then you throw it into a black hole, and then you wait, and then the black hole evaporates. Whatever is coming out, I don't know. And then the black hole decays. And the question is then what remains? And since this radiation here cannot carry this charge Q, because the horizon doesn't know anything about the charge, it's not a gauge charge that has field lines or anything. The black hole horizon only knows what the mass of the black hole is. Or if you say that you have electromagnetism or a charge, knows about the electromagnetic charge and the black hole, so it cannot emit particles with charge Q. In order to have the conservation of charge, you need to have some kind of remnant that has this charge Q. And now the argument is that you can play this game as many times as you like and throw as many charges of charge Q into a black hole, in multiple black holes, and this would mean that you would have some infinite number of remnants. Each of these would have some kind of charge under this global symmetry Q. And then the problem is, people are claiming that this is now a problematic situation. This is now again disputed, and there are people claiming that it's not necessarily problematic. The more convincing answer I got was that, okay, if these remnants were there, we would have to observe them, but we don't. So they should not be there. And this is an argument against having these global charges. Of course, now this whole argument breaks down if the symmetry is not continuous. And the other way that this symmetry breaks down, this argument breaks down, but in a way that is favorable for us, is that the symmetry is being gauged. And now we can detect the charge from far away. And you don't have the problem here that the horizon is blind, let's say, to the charge anymore. So this would be a way to go around. So global symmetries are bad, gauge symmetries are still fine.
May I interrupt? Because I think this whole argument is based on the fact that there is a singularity and nothing happens in the singularity. But since we don't really know what is happening in the singularity, I think, for example, if you admit the fact that there is not a singularity, but some sort of transition, and then you transition to another something, then you shouldn't have this problem, should you?
Yeah, I cannot counteract this. I'm saying this is a very, very crude argument that you can punch many holes at. But take it as a working hypothesis that you don't want to have these global symmetries then, and how well you can motivate this or how well you can convince yourself, then this is debatable,
Okay,
let's say.
Sorry, can I ask something?
Yes?
Can you please explain a bit what do you mean by global symmetry and gauge symmetry and what's their difference? Like
Okay.
Yes.
Okay. The gauge symmetry is a symmetry that you can measure no matter how far away you are, because you can always have some kind of field lines that are going away. If you have some field, even if it's behind the horizon, you have the charge here that is a gauge charge, and then you have the field lines that end up on the field. So you go here, you do Gauss law around outside of the horizon, and you still have the field lines coming in and out, and then you can measure what is there. So think about it as electromagnetism. There is some propagator of the force that is traceable. The global symmetry is nothing. It has no way to interact with the outside world. It's think about, I don't know, what do they say that the standard model has, the global B minus L or something. There is no way to measure what the baryonic charge is.
Okay, good.
Without actually interacting.
Okay, nice, thank you.
Okay. And now they play in the, okay, sorry, I forgot my references. Okay, this Cobordism idea, okay, it's math, I'm not citing anything. But then the next thing, the whole idea I'm following here about the global symmetries, and the next argument and the conjecture that's coming later is based on this paper by Jacob McNamara and Kumunivasa in 2019. And they claim that the requirement for quantum gravity is that these groups are always vanishing. And the idea and the reason to claim this is that then you can kind of, if you have these Cobordism classes, these classes are characterized by some specific Cobordism invariants that would be there no matter what you do in your theory. And then they say, suppose I have a manifold that is of dimension k, and then I glue it to some other spacetime, and this is some manifold mk, and this is rk, and they say they do this union where you cut off some small circle here, and you glue the manifold on the Minkowski space, and then you say you go very, very far away, and then you try to look at it, and you only see the flat space. So you have some gravitational soliton, but the charge is global. Because of the reasoning above, there is no field line, there is no way to detect this Cobordism charge from far away. And then they say you can play the same game, you can throw your gravitational soliton into some kind of black hole. Okay, how you build your black holes is up to your thought experiment once again. And then they say, okay, this would mean that your Cobordism invariant is defining some kind of global charge. And this charge corresponds to a global symmetry. This is bad, so we want to avoid this situation, so we impose this condition here. Very hand wavy once again, but the good thing with this statement and this type of statements in general is that they have very strong predictive power. And actually this is being used. They have shown several examples that this can predict things that we already see in string theory and we expect to see. And they can also make predictions about things that we don't directly see or we don't know how to describe at this point. Okay, so to be a bit more precise.
What's the meaning of a global charge in that case? That you have a manifold glued in space?
The global charge is that, okay, think of all these things are compactification manifolds. And then they say all the theories of quantum gravity have to be in a trivial Cobordism group. So everything has to be united to the vacuum. The vacuum means that there is no consistent compactification down to 0 dimensions, effectively. So nothing, there is nothing there. So you need to have some way to kill your theory in any case. And they are saying that, okay, if you have some kind of non-vanishing charge, you cannot do this. You cannot go to nothing. It's prohibiting you to go to nothing. And
This whole story I kind of understand, but what's the meaning of the word charge in the case of a non-trivial space here? Like,
the charge, it's the label you put on it, I would say.
Okay.
The charge can be the flux that is going through a brane if you have a manifold. It could be a Chern class, for example, in actual examples. It's some kind of topological invariant or something like this, but it's
okay.
since you allow.
So it's not literally charge is a number kind of that's invariant.
Yes, it's a generalized kind of charge. I don't know if Nicola has any disagreement with that or can explain this in a better way.
No, it's fine. I think I understand. Yeah.
Okay. Okay, so the idea is that, okay, you compactify your theory in this k-dimensional manifold, and then if you want the class to be 0, you need to have this k plus 1 dimensional manifold that is closing off your spacetime and it has boundaries and it's nice and round, let's say. So from the point of view of the full theory, you have a d minus k plus 1 defect. And now the claim is the following, that all these compact closed K manifolds are associated with this d minus 1 minus k. Sorry, this, okay, defects, and now you have the Cobordism invariants that are the so-called charges. And you want everything to be, since these charges would be global, so bad in the sense that we cannot accept them based on our assumptions of the theory, let's say, we require that these groups are always 0. But then the thing is, okay, let's go back here, for example. I told you that this is a good approximation, let's say, for type 1, and then we are seeing multiple classes that are not 0. So the idea is that effectively spin here, or spin C in other cases, or spin class for theory, or whatever your actual spin structure you're working with is not the actual quantum gravity spin structure. So they are saying that instead of working with the quantum gravity structure, we're working with some modified quantum gravity structure, and this is the reason that we have these non-vanishing classes. So if some group here is non-vanishing, then we have two options. We either break the symmetry. What does this mean? It means that the non-vanishing class is this manifold that cannot be capped. So effectively, you are introducing a defect or something that allows you to close off the space-time. And I will give the explicit example about this. And our paper is a very explicit construction on such a defect.
Sorry, Andriana, can I ask
Yes?
something?
Mm-hmm.
Because I was disconnected for a few minutes. How is this connected with the global charges?
The Cobordism invariants of non-trivial class would be global charges, and we don't want them, let's say.
Mm-hmm.
So we want to impose that we are in a trivial Cobordism class, and this is also related to the fact that the quantum gravity is claimed to be a unique theory. And this was one of the motivations, sorry, I forgot to mention this. When they started this paper, they were saying, okay, for example, we have type 2b, type Y, we know that these are T-dual to each other, so there is some deeper connection. But do we say that these are the same theory? No. Or you have the start of the 5 superstring theories, and there are dualities, there are ways to go from one theory to the other. But they want to somehow quantify what it means to be in a unique quantum gravity theory. And since each of these theories you can get by compactifying on some kind of manifold, and even to the point, so you don't compactify at all, if you impose that all these Cobordism charges are trivial, you impose that you have a single theory of quantum gravity. And this is the deepest motivation, let's say, behind this.
Okay,
I don't know if this helps.
Yes. But in the well understood cases of string theory,
Yes.
Cobordisms are associated with global symmetries one by one? Is that well established? So if that is the case, what do you gain by studying cobordism instead of just doing the usual compactification and counting the groups?
You can even predict things. You can predict things here, because now they are claiming, for example, type 2A and type 2B should be connected. So there should be some kind of domain wall defect between these two theories. And there should be some supersymmetry breaking defect. But we don't know what it is, but we predict its existence.
Mm-hmm.
There are much deeper reasons to see, for example, some kind of bottom-up approach for the tadpole cancellation without imposing string. It's a very deep mathematical structure, I would say, and it's very beautiful to study it in this framework, and it's very robust. It's giving you, for example, instead of doing the compactification, we can study, let's say, the Cobordism group of a space instead of the point. These are all the Cobordism groups of the points, and then what is coming out effectively is the branes that are allowed. And it's coming out on its own. You don't need to impose that in type 2 we only have 7 branes and 9 branes and odd dimensionality of branes, but it comes out automatically. So it's a framework that has the power to describe everything, I would say. Now, if we know how to interpret it correctly, it's up to our skills, probably. Okay. So thanks. The one option was breaking the symmetry. Any other question at this point, or? Okay.
Can you say again what this QG tilde was? It's kind of lower than the QG, or so it's closer to what we see see?
Very good. Okay. So, for example, in the case of breaking, you say that instead of being in sorry, let me proceed to my next note. Okay.
So just before, because you talk about breaking, so for example, this is consistent with Goldstone theorems, etc. Can you reproduce Goldstone theorems from cobordism, I suppose?
This I don't want to say anything about this. I'm not aware of some explicit study of that. I don't know if anyone else in the audience knows.
I'm not sure if it's supposed to be spontaneous breaking rather than inserting some sources that break the symmetry on the nose. Like, I'm not expert.
Yeah, what we have here is yes, on the nose breaking.
Because in the standard calculation of global symmetries, breaking Goldstone theorem plays an important role. I don't know if you can see a similar thing in the cobordism discussion. No, I'm just curious. Maybe the question is irrelevant, but since you said that cobordism is related to global charges, and the traditional way of studying global charges is by, say, symmetries, which can be broken, and you know the stories. You can go to the Higgs phase, to the Goldstone phase, etc. There is a well understood mechanism of doing that. Now I wonder whether there is an equivalent discussion using this mathematical language, cobordism. That's my question.
Not as I know of, but this doesn't say anything. It means I don't know of it. I don't know. But it would be interesting to actually see if this is there indeed. Okay, so to write down more explicitly what this is, the breaking is saying that you include the defect, so you change your structure to some structure that includes the defect. And effectively, the classes that are being in the kernel of this map, I don't know, let's call it row. These are the classes that are being killed. So this QG tilde is some kind of first approximation you make to the true quantum gravity structure, and then you had ignored your defect. This was causing you to have some groups that seem to be vanishing, but in reality, in the full theory, would not be vanishing as soon as you included the proper defect. And this can even be like partial. So you have some group that is, I don't know. It could be that omega-1 of QG tilde, let's say, is Z, and then omega-1 of QG tilde plus defect is Z2. So it means that you have killed some of the charges and not all of them, and then you need another mechanism or a different defect to kill the Z2 charges, or you need to do something else to approach even more the true quantum gravity structure. And the other option then would be the breaking, the gauging, sorry. And now the gauging says that in order to have the full theory, consistently compactified on some manifold MK, you demand that the specific manifold MK is in the vanishing class. And this is called, let's say, the way I think of it as gauging is that you impose that now your charge on this compact manifold has to vanish. And this is the analogous of the typical vanishing of, I don't know, electromagnetic charges in a compact space or something. So you select, let's say, the manifold that is satisfying this vanishing of the charges in the compact space. And you can also write this down in terms of a map. And since now you are gauging, you have to include the gauge field in the spin structure. That's gauge field, and this is a map now in the opposite direction, let's say. And now the gauged classes are being co-killed. In reality, what this means here, for example, is that in principle, you would have a current and you would write down some cancellation of the current, and the right-hand side would be 0, and you add something, so the right-hand side is some delta contribution from some localized source or your defect or whatever, so the symmetry is not there anymore. And for the gauging, you put, a similar mechanism. Okay, so the advantage of this whole procedure is that it's very, very predictive. And the easiest things, for example, you can do is predict, okay, as long as I have a theory that is oriented manifolds and then I turn on B-form gauge fields, there is some kind of Cobordism charge that is satisfied. And now the structure here is oriented and B-form gauge fields, and the group that is one can compute these days, it's Z, and it's actually given just by the flux over some P+1 dimensional cycle. And this is the usual setup you have in type 2B or any compactification. And then you can play the game of identifying what the dimension of your defect should be. And then you see that you need to have some object that turns out to be the D-brane. Just very hand wavy again. So just by demanding that the Cobordism group is vanishing, and the fact that you have these Ramon gauge fields, and you also put it as an input in the Cobordism class, you get that the D-brane should exist. You predict their existence, and this is a very sensible prediction to make. The other interesting thing is that pretty much all the defects you can predict, and you know what they are, so you have your actual realization matching your prediction are supersymmetric. But the problem is that when your defect has to be breaking supersymmetry, this is where you lose control over your theory anyways. So this is where you wouldn't have access to, and you don't really have a good description for that. But Cobordism can predict what the properties, let's say, of this defect would be. It would be the dimensionality, or it would be that it is charged under Z2 or whatever. And this is an option, a reasonable way, let's say, to gain access to this non-easily approachable regime of string theory. So non-supersymmetric.
Just a question. Sorry. So here your input is that you force your system to have a U1 gauge symmetry, and your cobordism predicts that it should be a D-brane. Is this correct?
My input is that I want to have to compactify on orientable manifolds, and I want higher p-form gauge fields to exist. So I'm putting this in the way I'm computing my cobord. It's a bit more complicated to put this additional structure. And then what comes out of it is that there should be some p+1 dimensional object that should be charged under the field that I put in as an input.
Which is U1, right?
Yes, it's U1.
Okay, yeah, thank you.
Okay.
Can you say again what's wrong with supersymmetric defects? So
we don't know them. So, for example, they are claiming they have
supersymmetric defects.
Supersymmetric. Supersymmetric, there's nothing wrong. They are fine, but you already expected what they are. They would be some kind of D8 brane or an orientifold that you know how to write down, and you can write down a boundary state. You can describe it in a very concise way. This you know. The non-supersymmetric branes, you don't really know how to describe. But this is more like, observation, not a fundamental reason, I think, that, or it's at the edge of our computational abilities.
But what's the problem in this setup with the supersymmetric defects? Like they don't do the job that you want them?
No. Okay. In the cases that we need the non-supersymmetric ones, usually you are not allowed to have the supersymmetric ones just because you know that you need to cap off one dimension of spacetime, so you need to break Poincare invariance. So if you're already breaking Poincare invariance, you cannot have, and translation invariance, you cannot have supersymmetry.
Okay.
So you need to at least partially break supersymmetry, and then they have just a list of all the theories you have, and they say, is there, a partially broken supersymmetry below what I have? And the answer was no. The thing that was immediately, it was n equals 1. You cannot partially break n equals 1. You just go to 0.
Okay, thanks.
Does that make sense?
Yeah.
Okay, good. Okay, and then the idea is that since we need to study these non-supersymmetric setups, and this was actually the observation or the framework introduced by the group in Madrid. So this is what is called dynamical cobordism. And and it's the part 3 of the talk now. Okay, I'm not running out of time. So the idea is that in many frameworks where you don't have supersymmetry, you have potentials that look like this. So there is some kind of exponential contribution to the scalar potential. Whatever, I will write down a specific action later. And the idea is that while usually when you write down, I don't know, you do some compactification and you want to be at Calabi-Yau 3 times Minkowski 4, and you expect to find some kind of potential like this. Here is the potential, it's at 0, so it means that this is indeed the Minkowski, and we can have this separation of the tensor product between the internal and the external space, and the internal space can come out to be maximally symmetric if you are at some minimum of the potential or maximum of the potential. But the idea is that there exist these solutions that these setups that they call tadpoles. Let's say, okay, let's give some credit to these people. So this is not the usual tadpole that one encounters, let's say, for Ramon charges that you need to put the equal number of branes and anti-branes so the charge cancels on the compact space, blah, blah. What they dub as tadpole is these potentials that have this contribution to the potential that looks exponential, and they are not at a minimum. So we have some kind of running solution. And this was, okay, let's say, Uranka et al. 2122. So there are 3 papers by the group in Madrid on this type of setups. And the idea is that this type of potentials you encounter in non-supersymmetric setups. And there are 2 main very well-studied models, so one more than the other. So the first thing is the so-called Sugimoto model. And the idea is that you have some kind of type 1 theory, and you have a stack of D9 and anti-D9 branes. This was studied by Sugimoto in 1999. And he's saying that let's have a stack of D9 and D9, and then just put some pattern factors on them. And if you choose the groups to be USB and USB. In order to have a consistent model, you need first that the anomalies are vanishing. So this you do via Green-Schwarz. And this is given just a condition M minus N has to be 32. And then you also you want to kill the tachyon that is developing between the branes and the anti-branes, and this is forcing your theory to have no branes at all. So M equals, this was a mistake. It was N minus M. So this is forcing M to be 0, and you have a theory with 32 anti-9 branes. And then you need to cancel their charges, so you need to include some kind of Orion default. But now this is not the usual Orion default of type 1. And this is what is causing, let's say, the problem. And this Orion default needs to now have positive charge and positive tension. And since these are negatively charged, then you need to cancel the whole charge on your theory. You have these special Orion defaults that are adapt O++. And these have now a positive tension. So effectively, when you write down now your action, you will have something that looks like, okay, let me write down the first equation of the whole talk. Just the usual stuff you would have. Here is the dilaton, and now you have these 9-dimensional objects. Here, this is N plus 32, where N is, okay, small n. Small n, maybe small n. And this is an auxiliary field related to the anomaly cancellation. So this is saying effectively that you have to say that N equals 32. Okay, capital N probably is N minus M here. And to have the anomaly cancellation, but this means now that if your capital N is 32, you cannot get rid of this thing. So your potential effectively has this contribution that is precisely of this type, and you have this type of tadpole exponential runaway solution. And it's not trivial to find solutions to this type of setups. This was initially found by Dudas and Murad in 2000, probably 2000. And the particular thing in the solution is that it's a solution with spontaneous compactification on the circle. So then comes, okay. And this is not trivial at all. This type of models were also studied a lot. I think there was a lot of motivation to study these models because they were kind of explaining the number of large extra dimensions, and they were giving some physical reasoning for the compactification without imposing it a priori, because we want to end up in a theory with a smaller number of large extra dimensions. How much time I have? 10 more minutes? Yes, okay. Okay.
Yes.
Okay, perfect. And then comes the second model that I will introduce later. So, okay, the second model, let's say, would be the T-dual of this Sugimoto model. And the idea is you already have the circle, so you can play the game of the usual compactification, the duality, and so on and so forth. And this will be the starting point for our explicit Cobordism setup. But okay, why do the Madrid people say that this is now some kind of dynamical Cobordism? The whole claim by them is that the spontaneous compactification that's happening, or you have some kind of finite length in your solution. There could be singularities at specific points, so the distance between the singularities, so the length, space-time length for which you can transfer your solution is finite. And what they are claiming is that, okay, you have these two things. If there is a dynamical tadpole T, and by T they just dub this factor here. The solution extends in this finite distance, and this is scaling in a specific way with the tadpole. Finite, and they have this scaling relation, delta to the minus n is scaling like T. And the mechanism that is behind this is the Cobordism defect. So the reason that your space-time is finishing is that in reality there should be some Cobordism defect in the end that is capping off your space-time. And I will be more explicit in our specific realization, let's say, of this thing. Cobordism mathematical theory is space-time. And they even claim that, okay, curvature can be also expressed in such a relation, and this is e to the minus delta over. And this is not particularly important. They propose specific scaling relations that have to do with the tadpole. Okay, so this is the whole claim. You have some theory that has a tadpole. Probably the reason for the tadpole is the lack of supersymmetry. This theory turns out to have solutions that have a finite length, and then finite length is indeed a realization of Cobordism in explicit setup. And now let's say we provide a complete realization of this. This idea. So our setup was inspired by this T-dual of the Sugimoto model. Okay, I will not write it down, but the reason we're studying this is that the solutions were identified by Ralph and Anna Maria Font. So we had a very good idea what the solutions are. And indeed, they could find in this T-dual of the Sugimoto model also solutions that have a finite interval. I have a circle plus one more direction of a finite interval. But we started a more agnostic approach. And we say, okay, let's decide that we want to study what the back reaction of okay, it's neutral, non-supersymmetric. Now, non-supersymmetric is going to be related with the fact that we will break translation invariance effectively. Non-supersymmetric 90 domain wall. And this can be anything. This description is matching, for example, a non-BPS D8 brane. And non-BPS D8 branes don't have an explicit description in terms of a metric, not something that was known. And it's something that we are claiming that we might have achieved. Or it could be the stack of orientable planes with positive tension and anti-branes, as in the Sugimoto model. But this is here, we are being quite agnostic at this point. So we make an explicit answer for the metric. Ry. Now, y is what is, okay, R is conventionally the 10th dimension of the space-time that we expect to be spontaneously compactified, and is the one that is along the brane, and y is the direction that is where the brane does not extend. So you see here we have this kind of anisotropy that we are imposing. So one of the directions that is linked to the brane is not behaving as the rest. So this is breaking supersymmetry explicitly. And then the action would be very similar to what we have here. I will not write it down again due to constraints of time. And you have this answer, you solve everything, you can find solutions. And the thing is that we have two types of solutions. Solution one indeed has this R going around in a circle, and then y is becoming an interval, but this interval has a proper length that is infinite. So in principle, it's just usual space-time direction. And we also have singularities, and this is the usual thing that is one comes across in this type of solutions. And the singularities are in R, and the warp factor is whatever, is going like logarithm of R minus the location of the singularity. This is not important, it's logarithmic singularities. And infinite length. And now the idea is, okay, can we treat this as a Cobordism defect, or do we expect to see a Cobordism defect there? And the important point here is that no, because we have y being infinite, and the Cobordism defects would have to be at the end of this interval y. So this means that this is not a consistent way to view this problem. So there must be something else wrong with this setup at this point. But the good thing is that we have this different solution. Okay, we had two solutions plus minus due to naming of parameters, but the interesting one is the solution 2 plus. And this solution 2 plus had R being compactified on a circle, but now y was becoming an interval of finite length. In principle, okay, it doesn't matter what the length of this interval was. So now we had the setup was effectively looking like this. We have here, let's say, R. This is a lattice effectively because it's compactified, or you can view it as the circle. And at R equals plus R equals R, you have here your brane. You locate, this is some choice you make already when you write down the metric. And then the thing is that here, this is the y direction, and this is now finite. And in principle, you can study your solution, and the geometry of your solution is like this. So you have the circle here, and the radius of the circle is y dependent. And since you have finite length, you expect that you can place your Cobordism defects exactly at the length, at the ends of this interval. Since your topology now is, I don't know, S1 times interval. And this is the expectation. And now, how to view this in terms of Cobordism groups. And now let's say, okay, probably we have the circle here, so this could be related to the Cobordism groups of the circle. So let's look at the omega-1 spin. Spin because we are in type 1. And so you see that this is Z2. So it means you need to break it somehow, or you need to gauge it somehow. And the idea is that in order to break it, you have to have the defects, you need to place something there. So the solution that can be broken is the solution 2 plus. But what about the solution 1 that now is at infinite? This is not finite and you cannot place the defects. And the idea there is that you can claim that this solution can be gauged. So what you say is that there is some problem, and the single d-brane that I have, or the single, I don't know if it's a d-brane, the single offset that I have is not consistent. And what I should do is that I require that this Z2 charge is vanishing. So I need at least pairs of them. And the object that in physics is realizing this thing is the non-BPS D8 brane. So you can claim that if this object indeed is a non-BPS D8 brane, the fact that we find the singularities that are spoiling the solution is to be expected, because the single non-BPS D8 brane is not consistent. The Cobordism charge is not vanishing, and this is not something we should allow. We should only allow setups where the Cobordism charge is vanishing, and this is happening for an even number of this type of objects. And now for the other one, okay, you need to put some defect, but what is the defect? The defect, since this omega 1, you need to have this d minus k minus 1 defect. So this has to be an 8-dimensional brane. So it has to be some kind of 7 brane. I don't know if it's a D brane, probably not the D brane, because you need some supersymmetry breaking. You need some kind of 7 brane. And then you play the same game again. I'm running a bit over time, I'm sorry. So the idea is that you write down once again an action about with this 7 brane object now being coupled. So effectively what is happening is related to what you had. I missed the delta factor. Okay, in principle, when you write down the delta brane, there is a delta factor that is running around only 1 dimension. This is now a codimension 2 object. You write down your action. You study the solutions. You have to impose that the solution now is anisotropic. But you should not break AD Poincare invariance, because if you break AD, then you create singularities in the 8th dimension. So your 7 brane should be good, let's say, enough in all the 8 dimensions, and then the 2 perpendicular directions, you choose to break anisotropy, because only in this way you expect to find some solutions. You play this game, you make these answers for the metric that I'm not going to write down, and the idea is, and the important result is that you can actually find solutions. You study the solutions. These solutions have singularities of the exact same logarithmic type. The solutions have positive tension. So we have all the arguments to claim that if you place together this 8-dimensional object, there is a pair of 7-dimensional 9 and 8. Sorry, I was using the 7 brane convention without measuring the time thing. So in principle, in our setup, let's say, if you choose solution 2 plus, you can place 2 solutions tilde, which are the solutions of this 8-dimensional thing now, here in the singularities, and this is curing the defects. So you get a setup that is, as one would expect, no singularities anymore, or at least they can cure the singularities, and this is consistent with the fact that we have put the defect that is explicitly breaking this Z2 factor, and we have managed to kill the global charge, or at least we claim so. Okay. I think I will not say anything more. I'm already a bit over time. I'm sorry about this. But I hope I have convinced you that Cobordism is very useful, very interesting, and I don't know. Please, any questions, I would be happy to answer.
Okay, thank you very much for this nice talk. Are there any questions from the audience? Yes.
So this is supposed to be a non-supersymmetric situation, okay? So you have broken supersymmetry, but
Yes.
how can you check the stability of this construction so that you can convince somebody that this is really viable?
Okay, for example, the string Hubble constant is fixed by your selection of parameters here, and there is only one selection you can make to put the branes in the correct place, and the singularities come out with correct scaling so that they can cancel and everything. And GS is indeed smaller than 1, so this is one thing that is good enough. Now, the fact that there might be quantum corrections or anything else, this is, yeah, I'm not sure how this would be concretely claimed, that there are no corrections that would change the stability of this. But I don't know, Nicolò, are you there?
Yes, but
do you have a better answer?
Not really. So in these setups, you are typically also off shell. So it's not clear if there is a vacuum at all. But this cobordism or K-theory can detect charges which are supposed to be stable objects in this case. So these objects should exist, but indeed one should have another setup probably in which the same object appear, and then can double check at least.
So cobordism is something which is very it's non-dynamical. It's like a group theory. Is it the way I understand it? So you measure objects which are supposed to be protected by some symmetry. Yes. Okay.
I would say it's on the same footing as using K-theory for brains.
But you don't know whether, what is the dynamics of these objects. I mean, most of them are non-perturbative in any case, like the brains. But yeah, that's very interesting. So what could be one of the claims would be that regarding quantum gravity in the absence of global symmetries, the aim would be to design models where they don't have global symmetries. How could you imagine proving that there is no global symmetry in quantum gravity? I mean,
I would say this is twofold. One part of it is that if you find some theory that you have no way to cancel the charges, then you say, it's in the swampland and it's not a good model. If you have some reason to say it's not a good model, right? If you try to compactify type 2B on a circle and you find a non-vanishing cobordism search, it's clear that the cobordism group that you're looking at is not good, so you need to look at a different cobordism group. So this means you add the defect, or you add gauge fields, or you do something. So this is a guiding principle towards the true unique theory of quantum gravity. And this you should be able to play the same game to everything, and this QG tilde every time should be approximating even better and better and better the true quantum gravity group. And in principle, every theory should lead to the one that has every group vanishing.
So do you expect that this is a unique...
Yes. And this is the definition of, let's say, saying that the group is vanishing. The group is vanishing, so there is only the trivial class. Every theory of quantum gravity should be related to each other via some kind of domain wall or topologically allowed transition. This is very vague, but yes, the idea is this.
And how does this fit with the swampland in the sense that with the enumeration of the quantum gravity of the string theory vacua? Does it fit with the numbers?
Yes, I would say so. The numbers, the swampland is indeed claiming that the number is much smaller than the expectations, right? So it should be very restricted. And then depends what you're counting, because effectively what you are counting right now is one vacuum of string theory is type 1 compactified on a Calabi-Yau with H11 275 and H21 276. And then if there is a Calabi-Yau with, a Hodge number that is slightly different, this is being counted as a different vacuum. According to cobordism, this now should be the same vacuum, the same theory. So this is in cobordism 1, in string vacuum accounting 2, let's say. But it's the same theory on the 6-dimensional manifold, and all the quantum theories of gravity on any 6-dimensional manifold should be the same at the correct level.
In that sense, all vacua should be the same, right? Because you claim that everything is cobordism. Yes.
It's a unique theory of quantum gravity. I don't know. Do you want to call it M theory? Do you want to call it?
Okay, that's a noble ambition, but I still haven't understood how two different things in string theory, you claim they are actually the same. What do you mean the same? But
it can be connected by a finite action, let's say. You need a finite amount of energy to transition from one theory to the other, or to create some bubble in your theory. In my theory here in the room, I can create with some finite energy a vacuum which is type 2b. And here I'm in type 2a, and I can go into the bubble with a finite amount of energy. If it's finite, it means that there is some manifold that is connecting the theories and they are cobordant. The problem would be if you would need an infinite amount of energy to perform this transition.
Yeah, I would like to know if there is a precise, say, field theory example, like the one that you mentioned, where in the standard field theory approach, we have two vacua, and you can show that they are actually the same. Is there a toy model that two different vacua, like in the string theory?
This they do like quite a lot with these bubbles of nothing, and even the sitter bubbles, and you create a bubble and you use this in wall approximation, and you have the sitter in your vacuum, and then this is decaying, and then the cosmological constant inside the bubble becomes something a bit lower and lower and lower, and then until it decays to the cosmological constant of the background. But this setup exists, and it's very well studied, I would say, as far as I know. What else now? These cosmological bubbles, and they even have these bubbles of nothing, but they are claiming that you can create this bubble that has nothing inside, and you can propagate this vacuum, this bubble in space, and see what happens and whether it shrinks or expands or whatever. So these types of setup exist. There is this in string theory, this Horava-Witten brain, but I'm not very familiar with. I don't want to say something, but they are claiming that this is a constrained setup where we also transition from one theory to the other. But for this, I would refer you to the original paper.
Okay, thanks.
Or they have these other setups again in string theory. For example, you take F-theory compactifications, and you take this limit where the fourfold, like F-theory to type 2b limit effectively. So you modify your compactification manifold, and they say that this is indeed a finite energy domain hole.
Yeah, still I am
not convinced.
No, well, far from convinced, but this counting, it's okay. I suppose there are some reasons, but even more basically, one way to understand, one way to see this proliferation, this very big number of string vacua, is if you see the entropy of strings, that it really grows exponentially. So now, if you are claiming that some of these things are actually the same, how would you count? Okay,
it depends what you mean by the same, because right now what we are doing.
What do you mean by the same?
I agree, because right now we are starting, let's say, half of these vacua are coming from compactifications of type 2b, half of them are coming from type 2a, half of them are coming from type 1, three halves, okay, whatever. So your starting point is different. Now at least we are claiming that you get all these things, but the starting point is the same, one.
Well, it's
the vacua could be different, but it's one theory. And now if you want to interpret the vacuum as a different theory, because you measure at a different cosmological constant, then
you make the argument completely the other way around. Yeah, I understand that. That was the original idea of string theory: one Lagrangian, one theory. Then we start having an infinite number of vacua, but then. Okay, what does it mean to have a different vacuum from the other? That's my fundamental question. So yeah, that's a very interesting story. So if you connect two things, are there different configurations in the statistical space? Should I count them in the partition function? Should I not count them? It's like, is it cobordism? Is the idea that cobordism is like a gauging of global symmetries? So eventually you have somehow, I mean, if you have a gauge,
some redundancy, you mean?
Yeah, so then you indeed you have one vacuum, but you know, you have,
yeah, I understand what you mean,
like
but
a gauging of it's like a global gauging. Well, global. It's a gauging of the string theory compactification landscape. So indeed, if you have a gauging, then you don't have many vacua, but you have much fewer vacua, because all the vacua are related by gauge transformation. That's it. That could be one picture where you have in one where many vacua are related by a transformation, a gauge transformation. So eventually you have only, say, one real vacuum. It's like QCD. Well, you have a real vacuum, non-perturbative vacuum, but you have a gauge theory. Yeah, I don't know. It sounds very interesting. Yeah. But you know, my questions are naive because I don't know very much about this story.
No, not at all. I would say too deep, not naive at all. And yeah, the discussion is not reaching that level usually. It's we are, focusing on how to compute this group, or what does this non-vanishing group mean and how to kill it. But yeah, what is the theory behind it? And yeah, this is indeed something to be understood properly.
Okay, are there more questions? I guess not. So therefore I'm gonna stop recording now and then we can discuss. Okay.